Welcome to this problem-solving session. Today, we'll dive into problem number 1714 titled Sum of Special Evenly Spaced Elements in Array. In this problem, we'll explore how to calculate sums of specific elements in an array based on certain criteria. Let's dive right in and break it down step by step. In this problem, you are tasked with finding the sum of special elements in an integer array called nums. An element in the array is considered special if it satisfies two conditions. First, its index must be evenly spaced, meaning the index I satisfies the condition I%k equals 0, where k is a given spacing interval. Second, the element itself must appear exactly m times in the array, where m is another specified value. If no elements meet these criteria, the output should simply be 0. The input includes the array nums, which can contain up to 10,000 elements with values ranging from -10,000 to 10,000, as well as the integers k and m, which define the spacing interval and frequency requirement, respectively. The output will be a single integer representing the sum of all special elements. Let's look at some examples to clarify the problem. In the first example, the input array is 1, 2, 1, 2, 3, 1, with k equals 2 and m equals 2. Here, we focus on indices that are evenly spaced by k equals 2, which are indices 0, 2, 4. The elements at these indices are 1, 1, 3. Now, among these, only the number 1 appears exactly m equals 2 times in the entire array. Therefore, the sum of special elements is 1 plus 1 equals 2. This simple example demonstrates how to find evenly spaced indices and filter elements based on their frequency. In the second example, the input is 5, 5, 5, 5, 5, with k equals 1 and m equals 5. Here, since k equals 1, all indices are considered evenly spaced, so we evaluate the entire array 5, 5, 5, 5, 5. The number 5 appears exactly m equals 5 times in the array, satisfying the frequency condition. The sum of these special elements is simply 5 plus 5 plus 5 plus 5 plus 5 equals 25. This example highlights cases where all elements in the array may qualify as special. Now consider the input 10, 20, 30, 40, with k equals 3 and m equals 1. The indices evenly spaced by k equals 3 are 0, 3, corresponding to the elements 10, 40. Both 10 and 40 appear exactly m equals 1 time in the array, meaning they meet the frequency requirement. Adding these numbers together gives the sum of special elements as 10 plus 40 equals 30. This example emphasizes how spacing and frequency criteria are applied even when only a subset of the array is considered. Finally, let's discuss some edge cases. In scenarios where no elements are special, such as nums equals 1, 2, 3, with k equals 2 and m equals 3, the output should be 0 since no elements appear exactly m equals 3 times. Conversely, if all elements are special, like in nums equals 7, 7, 7, 7, with k equals 1 and m equals 4, the result would be 28 because every element qualifies. For single element arrays, such as nums equals 42, with k equals 1 and m equals 1, the output would simply be the element itself, 42. Lastly, for large arrays with up to 10,000 elements, the solution must be efficient to handle the constraints effectively. To tackle the problem, sum of special evenly spaced elements in array, we evaluated a few different approaches, starting with the brute force method. The intuition behind this approach is straightforward. For each index in the array, we check if it satisfies the condition I%k equals 0. If it does, we add the element at that index to our result. This process is repeated for all the groups, from 1 to m, to ensure every required summation is calculated. In terms of implementation, this involves using two loops, an outer loop to handle the m passes and an inner loop to iterate through the array and check indices. While this approach is simple and easy to code, its inefficiency becomes clear when the input size grows. With a time complexity of m*n, where n is the size of the array, this method can quickly become impractical for large values of n or m due to the sheer number of iterations required. Next, we considered an optimized approach that relies on pre-computing values to save redundant calculations. Here, we observe that the indices satisfying I%k equals 0 form an arithmetic progression. This insight allows us to pre-compute the sums for each such spacing pattern, or k-group, in advance. Instead of recalculating these sums repeatedly during the m passes, we build prefix sum arrays for each k group. Once we have these pre-computed sums, we can compute the total for any given query in constant time. The implementation involves first creating the prefix sums, which takes O, n, time, followed by calculating the sums for m queries, which adds another O, m. This gives us an overall time complexity of O, n plus m, a significant improvement over the brute force approach. Additionally, we explored using sparse indexing with hash maps to directly store and compute sums for only the relevant indices. While this method can also achieve O, n plus m, efficiency, it may introduce extra overhead due to hash-based operations, making it slightly less appealing for this problem. The final strategy we chose to implement is the optimized approach using pre-computation. This method stood out for several reasons. Firstly, it offers the best time complexity, O, n plus m, while remaining straightforward to implement. Secondly, the use of prefix sums is a well-established and reliable technique for solving problems that involve cumulative sums or repetitive range queries. It avoids the inefficiencies of the brute force method and is more structured and predictable than sparse indexing with hash maps. A key realization, or aha moment, during this process was recognizing that indices divisible by k form an arithmetic progression. This allowed us to systematically group elements and pre-compute their sums, eliminating redundant calculations. By leveraging these patterns, we struck a balance between efficiency and clarity, making this approach both practical and elegant. When comparing the approaches, we observed several trade-offs. The brute force method, while simple and easy to implement, is not feasible for large inputs due to its quadratic time complexity. On the other hand, sparse indexing with hash maps is efficient in terms of computational time but comes with additional memory usage and coding complexity. The chosen pre-computation approach offers the best compromise. It balances time complexity, memory usage, and ease of implementation, making it the most practical and scalable solution. By pre-computing prefix sums, we ensure that the solution remains efficient even for large input sizes, while keeping the implementation clean and manageable. In conclusion, this strategy not only addresses the problem requirements effectively but also ensures clarity and scalability, making it the optimal choice for this problem. In this problem, we are tasked with finding the sum of special elements in an array. A special element is one that meets specific criteria. It must be located at an index that is evenly spaced based on a given interval k, and it must satisfy additional constraints defined in the problem, such as being greater than a certain threshold. To solve this, the algorithm begins by parsing the input, which consists of an array ARR and an integer k that determines the spacing interval. For example, given ARR equals 5, 12, 7, 9, 21, 15, and k equals 2, we aim to compute the sum of the elements at indices spaced by k that meet the additional criteria. Next, we initialize a variable special underscore sum to 0. This variable will accumulate the sum of special elements as we process the array. To iterate efficiently, we use a for loop where the index increments by k, effectively selecting every kth element. By doing so, we limit our traversal to only the necessary indices, avoiding the need to check every element in the array. This approach ensures that we traverse the array efficiently, focusing only on the indices that are evenly spaced by the given interval k. After determining the relevant indices, we move on to applying the filtering criteria. For each element at the selected index, we check if it satisfies the given constraints. For example, if the constraint specifies that the element must be greater than 10, we use a simple conditional check like if ARR, I, 10. If the condition is true, the element is added to the special underscore sum. Once all the relevant indices have been processed, the value of special underscore sum is returned as the result. This approach has several key insights. By incrementing the index by k, we significantly reduce the number of iterations, making the traversal approximately n/k instead of n. Filtering the elements directly during traversal eliminates the need for extra storage or pre-processing. Overall, the algorithm achieves a time complexity of O, n/k, for traversal, with each filtering operation being constant time, resulting in an efficient solution to the problem. The algorithm uses minimal data structures, making it both time and space efficient. The input array itself is directly traversed, and no additional data structures are required. The only extra variable, special underscore sum, is used to store the cumulative sum of special elements, requiring just O1 space. Now, let's consider some edge cases. If the input array is empty, there are no elements to process, so the result should be 0. If the value of k is larger than the size of the array, the loop will iterate at most once or not at all, depending on the constraints. Additionally, if none of the elements meet the criteria, the sum will remain 0. To see how this works in practice, let's walk through an example. For ARR equals 5, 12, 7, 9, 21, 15, k equals 2, and a threshold of 10, we initialize special underscore sum equals 0. The indices traversed are 0, 2, and 4, as they are evenly spaced by k. Checking the constraints, ARR 0 equals 5 fails because it is not greater than 10. Similarly, ARR 2 equals 7 also fails. However, ARR 4 equals 21 satisfies the condition, so we add 21 to special underscore sum. At the end of this traversal, the final value of special underscore sum is 21. The algorithm can also be optimized further. For instance, if it becomes clear during traversal that no subsequent elements can meet the criteria, we can exit the loop early to save time. Additionally, if the constraints involve multiple conditions, we can pre-process the array to filter out irrelevant elements before the main loop. To summarize the final algorithm, we start by parsing the input and initializing special underscore sum equals 0. We then loop through the array, incrementing the index by k to access only the relevant elements. At each index, we check if the element meets the constraints and add it to the sum if it does. Finally, we return the cumulative special underscore sum as the result. This structured approach ensures an efficient and concise solution to the problem. Here, we begin by defining a class called solution and implementing the method sum of special evenly spaced elements. The method takes two parameters, an array ARR and an integer k, representing the spacing between elements. The first step is to check if k is greater than the length of the array. If it is, we return 0, as no valid elements can be selected. Next, we use a prefix sum array to optimize the computation of sums over any range in the array. This is achieved by creating an array prefix underscore sum, or each entry at index I plus 1 accumulates the sum of elements from the start of the array up to index I. After that, we initialize a dictionary modulo underscore sums, which will store intermediate sums for elements separated by k, grouped by their starting indices modulo k. We then iterate through each valid starting index, ranging from 0 to k1. For each starting index, we initialize a variable current underscore sum to track the cumulative sum of elements taken at steps of k, and we store these sums in the modulo underscore sums dictionary under their respective starting index. Using this approach, we systematically collect all relevant sums for each modulo class. Now, once we have computed and stored the intermediate sums for all starting indices in the modulo underscore sums dictionary, the final step is to calculate the total sum of these values. This is done by iterating over each starting index in the dictionary and adding the sum of all its accumulated values to a variable total underscore sum. This gives us the combined sum of all special elements in the array that are evenly spaced by k. Finally, we return total underscore sum as the result. To illustrate the usage, we provide an example where the array ARR contains the integers from 1 to 9, and k is set to 3. When the method is called, it computes the desired sum based on the logic we just discussed and prints the result. This implementation is efficient and leverages the prefix sum technique, along with modular arithmetic, to handle the problem's constraints effectively. Here, we begin by importing necessary classes and defining our solution class. The main method we're focusing on is sum of special evenly spaced elements, which takes an integer array ARR and an integer k as inputs. The first step is to determine the length of the array, and if k exceeds this length, we immediately return 0 because no valid elements can be selected. Next, we use the prefix sum technique to optimize range sum computation. We initialize a prefix sum array with one extra slot to store cumulative sums, where each position I plus 1 contains the sum of all elements from the start up to index I in the input array. After that, we create a map called modulosums to store sums for each modulo class based on their starting indices. This will help us group elements that are evenly spaced by k. Finally, we iterate through all valid starting indices from 0 to k1. For each starting point, we initialize a current sum variable and prepare an entry in the map for that starting index. Then, we loop through the array, collecting elements separated by k starting from the current index, adding their values to current sum as we go. Once we've collected the sums for each starting index, we store the cumulative sums into the corresponding list in the modulo sums map. This ensures that all sums for elements spaced evenly by k are grouped together. Now, we compute the total sum of all these special elements. We iterate through each starting index in the modulo sums map, and for each list of sums, we add each individual sum to a total sum variable. Finally, we return this total sum as the result. To demonstrate the solution, we include a main method where we instantiate the solution class, define a sample array and spacing value, and print the result of calling sum of special evenly spaced elements. For example, with an array of integers from 1 to 9 and k set to 3, the method calculates and outputs the sum of all evenly spaced elements at intervals of 3. This implementation efficiently handles the problem by leveraging prefix sums and modular arithmetic to minimize redundant computations. Here, we start with a basic example where the input array is 1, 2, 3, 4, 5, 6, 7, 8, 9, and the step size k is 3. The first step in our solution is to set up the necessary variables. The length of the array, n, is 9, and we create a prefix sum array initialized with zeros, having a length of n plus 1. This prefix sum array will help us efficiently compute sums of subarrays in constant time. Next, we calculate the prefix sums by iterating through the input array. At each index, we add the current element of the array to the sum at the previous index in the prefix sum array. For instance, at index 1, the prefix sum is updated to 1, at index 2, it becomes 3, and so on, until the prefix sum array is fully populated as 0, 1, 3, 6, 10, 15, 21, 28, 36, 45. This array represents cumulative sums, making it easier to retrieve sums of any subarray later in the process. Now, we proceed to traverse the array based on starting indices, grouped into modulo classes determined by k. We initialize a dictionary called modulo_sums to store these sums for each starting index. Beginning with start equals 0, we collect elements at indices 0, 3, and 6, which correspond to every third element starting from index 0. Adding these values produces the sums 1, 5, 12 for this group. Similarly, for start equals 1, we collect indices 1, 4, and 7, yielding the sums 2, 7, 15. Finally, with start equals 2, we gather indices 2, 5, and 8, resulting in sums 3, 9, 18. Once all modulo classes are processed, we compute the total sum of these special elements by summing all the values stored in modulo_sums. Adding these together gives us a total of 72, which is the output for this example. In this second example, we examine an edge case where the input array is small, containing just 3 elements, 10, 20, 30, and the step size k is 2. The process begins similarly with the initial setup. The length of the array, n, is 3, and we create a prefix sum array initialized with zeros, having a length of n plus 1. We then calculate the prefix sums by iterating over the array. Starting with 0, we add each element to the previous total, resulting in a prefix sum array of 0, 10, 30, 60. This array allows us to quickly compute the sum of any subset of elements as needed. Next, we traverse the array based on the modulo classes defined by k. We initialize an empty dictionary, modulo_sums, to store the sums of special elements for each starting index. For start equals 0, we gather elements at indices 0 and 2, which are 10 and 30, respectively. Adding these values results in sums 10, 40 for this group. For start equals 1, we only have one valid index, 1, contributing the value 20. Thus, modulo_sums 1 contains 20. Finally, to compute the total sum of special elements, we add up all the values in modulo_sums. This gives us sum 10, 40, plus sum 20 equals 50 plus 20 equals 70. Therefore, the output for this example is 70. Finally, we consider an edge case where the step size k is larger than the length of the array. Here, the input array is 5, 10, 15, and k is 5. In this situation, it is impossible to traverse the array with steps of size 5 because k exceeds the number of elements in the array. As a result, the algorithm immediately returns 0 without performing any further calculations. This ensures that we handle such cases efficiently without unnecessary computation. The output in this case is 0. To analyze the time complexity of the algorithm, we start with the prefix sum calculation. Here, we compute a prefix sum array, prefix_sum, which helps us efficiently calculate range sums later on. Since the array has a size of n+1, this step involves a single iteration through the input array ARR of size n, giving it a time complexity of O(n). Next, we move to the construction of modulo sums. The algorithm iterates over all possible starting indices, represented as start, within the range of 0, k1. For each starting index, it computes cumulative sums of elements spaced k apart. The number of iterations for each group is approximately n/k, and since there are k groups in total, this results in O(n/k), *k, which simplifies to O(n). This step ensures that we efficiently group and process elements based on their modular properties, eliminating the need for redundant computations. The next step is summing the special elements. Here, the algorithm processes the k keys in the modulo_sums dictionary. For each key, it accesses the pre-computed list of cumulative sums and combines them. Since the total number of elements across all these lists is equal to n, this operation also runs in O(n) time. When we combine these steps, prefix sum calculation, modulo sums construction, and summing the special elements, the overall time complexity is O(n) plus O(n) plus O(n), which simplifies to O(n). Shifting to space complexity, we analyze the memory requirements. The prefix_sum array uses O(n) space to store cumulative sums. Similarly, the modulo_sums dictionary, which holds lists of cumulative sums for each of the k starting indices, also requires O(n) space. This is because the total number of elements stored across all lists is proportional to the array size, n. In addition to the prefix sum array and the modulo sums dictionary, the algorithm uses a constant amount of space for auxiliary variables such as current_sum, total_sum, and loop counters. These variables do not depend on the size of the input, so they contribute O(1) to the space complexity. When we combine all of these components, the prefix sum array, the modulo sums dictionary, and the auxiliary variables, the overall space complexity is O(n) plus O(n) plus O(1), which simplifies to O(n). To put this into perspective, let's compare the optimized approach to a brute force method. A naive approach would involve explicitly iterating through all possible indices, checking whether each is spaced k apart from the previous one, and summing the elements. This would require nested loops, leading to a time complexity of O(n*k) in the worst case. However, the space complexity of the naive method would remain O(1), since no additional data structures are used. In contrast, the optimized implementation achieves a significant improvement by reducing the time complexity to O(n), while maintaining a space complexity of O(n). The efficiency of the optimized approach can be further understood by examining the best, average, and worst case scenarios. In the best case, when k is small or close to 1, the algorithm processes the array in a single pass, resulting in O(n) time complexity. On average, the complexity remains O(n), because the algorithm's performance depends only on the size of the input array and the spacing parameter k, not on the specific values in the array. Even in the worst case, where k is large, the processing remains proportional to the array size, maintaining an O(n) time complexity. This efficiency is mathematically justified by the use of prefix sums and modular arithmetic. The prefix sum array allows range sums to be computed in constant time, O(1), avoiding the need to repeatedly iterate over elements. Additionally, grouping indices by their modulo k ensures that the array is traversed a single time, regardless of the value of k. In summary, the optimized approach achieves both linear time complexity, O(n), and linear space complexity, O(n), making it a highly efficient solution compared to the naive alternative. When solving this type of problem, there are a few common mistakes to watch out for. First, be careful about how array indexing is described in the problem. Many programming languages, like Python and Java, use zero-based indexing, but the problem statement might describe indices as one-based. To avoid errors, always adjust your calculations accordingly, such as subtracting 1 when accessing an index. Next, edge cases are critical. You need to think about scenarios like an empty array, arrays that are smaller than the required spacing, or cases where no elements meet the specified conditions. Failing to handle these can lead to runtime errors. Also, inefficiency in iteration is a frequent issue. For example, if the step size allows you to skip elements, but you're still iterating over the entire array, this wastes processing time. Finally, always double-check how you're managing the step size. Forgetting to increment by the correct value, or using an incorrect step, can result in logical errors or even infinite loops in your program. Another point to consider is overflow when dealing with large sums. In languages like C++ or Java, using data types like int for very large numbers can cause overflow, leading to incorrect results. Instead, use a data type like long to ensure your sum can handle the maximum possible values. From an interview perspective, these types of problems often involve recognizing patterns such as modular arithmetic or arithmetic progressions. Spotting these patterns early can simplify your implementation significantly. Additionally, there are optimization opportunities. For instance, instead of iterating through all elements, you can use mathematical formulas like the one for summing an arithmetic progression, n/2*, first underscore term plus last underscore term. This approach saves time and makes your solution more efficient. It's also important to validate inputs before running your logic. For example, ensure the array meets the problem's constraints to avoid unnecessary errors. Finally, when discussing your solution in an interview, always explain your approach clearly, especially when addressing trade-offs like time complexity versus space complexity. This demonstrates your thought process and understanding of the problem. Now, let's look at some related problems that share similar patterns. For instance, LeetCode 448, find all numbers disappeared in an array, involves traversing an array while adhering to specific indexing constraints. Another example is LeetCode 189, rotate array, which focuses on array manipulation and modular arithmetic, a concept that's directly applicable here. LeetCode 1395, count number of teams, is another problem where you iterate through combinations of elements based on specific conditions, similar to identifying evenly spaced elements. Lastly, LeetCode 217 contains duplicate, emphasizes efficient handling of array-based operations and careful attention to edge cases. These problems all offer opportunities to practice the skills and techniques that are useful for this type of challenge. To solve problems like this, there are several approaches you can consider. The brute force method involves iterating through the array and manually checking each element to see if it satisfies the spacing and other conditions, summing up the qualifying elements as you go. While this is simple to implement, its time complexity is n squared if nested loops are involved, making it inefficient for larger arrays. A more optimized approach is to use iteration with a custom step size. By setting the loop to increment directly by the spacing value, you can skip unnecessary elements, reducing the time complexity to n/k, where k is the step size. However, this requires careful handling of edge cases, such as ensuring indices stay within bounds. Finally, if the elements form an arithmetic progression, you can use a mathematical formula like n/2*, first plus last, to calculate the sum directly. This approach is highly efficient, with a time complexity of 1, but it's only applicable under specific conditions, so you need to validate that the array meets these requirements first. Great job working through this problem. In summary, we tackled the sum of special evenly spaced elements in array problem by focusing on array manipulation and optimization. Remember to practice similar problems to strengthen your understanding. Thanks for watching, and I hope to see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!